Hi everyone. In part one, we left off doing a critical value approach for this particular problem. So we need to go to our F table and find the critical value when the degrees of freedom in the numerator are 2, the degrees of freedom denominator are 7. So we go to our table and we have 2. Let me erase what I had highlighted before. So we're particularly looking at this box of numbers, and our significance level is 0.05. So with 2, 7 at 0.05, it looks like 4.74. So our critical value is 4.74. And as you know, the critical value separates it into your reject and do not reject regions. And when you do the critical value approach, you then take your test stat, which was 5.25. We calculated that in part 1 of the video. Place it along the number line and see if it falls in that reject or do not reject region. And 5.75 is going to fall to the right of 4.74. So for this particular problem, we are going to reject. And you would follow it up with the interpretation. Of course, I didn't put a context in here that at the 5% significance level, the data do provide sufficient evidence to conclude that there is a difference in the means. It can just be stated very simply like that, because again, there was no context in that particular problem. What I would like to do is complete a problem where, again, you are given summary statistics. So here's a problem. You should hit pause for a second, read it. So as you notice with this problem, we are looking to see if at the 5% significance level, the data provides sufficient evidence that differences exist in a mean blood pressure drop for the 3 interventions. Those interventions are medication, exercise, and diet. Notice I did not give you the data values. I only am giving you summary statistics. On the test, I will only give you summary statistics. So you're not going to be able to just plug those data values into a calculator and pop out your answers. You're going to have to do some calculations. So that's what we're going to do in this particular problem. To start, though, the first calculation we need to work on, because notice you are given the mean of each population. There are 1, 2, 3 populations. What we don't have right now is the mean for the entire set of data. So we have the mean for 1, for 2, and for 3. To get the mean for the whole set of data, you have to consider that each of these populations are of different size. So the first one has size 5, and that was 11.4, plus 4 times 4.5, and then 6 times 7.2. If you do that particular calculation, you're going to get the summation of the data values. So then we're going to divide that by the total of n, which is 15. And we get an x bar of 7.88. That represents the overall mean of all the data. We're going to need that to do our calculations. So let's start with our degrees of freedom. Remember, first we look at the treatment, which is also known as the factor. When you're working with your graphing calculator, it's called factor. But again, you're not going to use a graphing calculator here because you don't have individual data values. The degrees of freedom of treatment is simply k minus 1, and you can go to your formula sheet at any time to see where I'm getting those degrees of freedom from. K minus 1 is degrees of freedom of the numerator. So k represents a number of populations. That would be 3 minus 1, which is 2. Now the degrees of freedom of the error. The error, of course, represents the amount of variation that's occurring within each population. So for that one, we're going to take the total n that we knew was 15, and we're going to subtract the number of populations, which is 3. So that's going to give us degrees of freedom 12. Now, the biggest calculations you have to do are the treatment sum of squares and the error sum of squares. So we're going to do that. I'm going to scroll this up and we're going to complete those down here. So the sum of the squares, treatment sum of squares, again, go to your go to your formula sheet. We are going to use the defining formulas for SSTR and SSE. So we're looking at the summation of each n and then the difference between the individual population mean and the total mean squared. So the individual n, so we start with first population is 5 times 11.4 minus 7.88 squared. Second population is 4, and then it's 4.5 minus 7.88 squared. And the third one is a 6, and it's 7.2 minus 7.88 squared. If you go ahead and do that calculation, you will see that SSTR comes out to 55.21. It's going to go, I'm sorry, not 55.21, I apologize. I was looking at it's 110.42. There you go, 110.42. Now, for SSE, go over to your formulas. We're doing the summation of n minus 1 times the sample standard deviation squared for each population. So this time, we start with population 1, which is 5. 5 minus 1 is 4. Times 2.9 squared. Second population has a size of 4, so that's 3 times 2.6 squared. And the third population, which has a size of 6, is going to be 5 times 3.1 squared. And that one comes out to 101.97. Put that in your block. Now, the rest of these calculations become a little bit easier. They're the two hardest ones you need to do, because the mean sum of squares is simply going to be the treatment sum of squares divided by degrees of freedom, which is 55.21. Then the error sum of squares is going to be the 101.97 divided by 12, which comes out to 8.5. So the table kind of flows nicely at this point, because for each of these, you're dividing sum of the squares of the treatment, sum of the squares of error by degrees of freedom. Then for your F test statistic, you're going to take the numerator of 55.21 divided by 8.5. We get approximately 6.5 for our test statistic. Okay, I apologize for any background noise. There's, due to the corona quarantine, there's a lot of different people in my house doing classes and having meetings and all sorts of stuff. So let's finish this one by doing our p-value approach. So I still like to draw the table, but this time when you do a p-value approach, remember that it is the test statistic that's going to go here of 6.5, and your p-value represents this entire area to the left. So to get our p-value, a couple things we need here. We need our degrees of freedom, numerator 2, denominator 12. We also need to know what our significance level is, of course. We'll need to compare that at the end. So let's see where we can find 6.5 on our table. Go to your F table. Degrees of freedom of the numerator is 2, denominator is 12. So here we have this block of numbers, and our 6.5 test statistic is going to fall between these two values, which means the p-value is going to be between these two areas, 0.01 and 0.025.
Yeah, so I think it probably comes right in at the uterus to go off.
So p is greater than 0.01, but less than 0.025. Alpha is 0.05. Clearly, you make that comparison. If p is less than 0.025, it must be less than 0.05, which means it is less than alpha. That is a small p, and small p's cause us to reject. Your interpretation, of course, is going to be at the 5% significance level, the data do provide sufficient evidence that differences exist in the mean blood pressure drop for all three interventions. Of course, it tells you there's a difference. It does not tell you where those differences are. That will be the next video when we take a look at the Tukey multiple comparisons.